Okay, so there they are back big. But if you draw yourself a few that are with straight sides, like the box is pretty easy to draw, pyramid's pretty easy to draw. This one, that icosahedron, is kind of hard to draw if you put all the dashes in there anyway. But the polyhedron have straight edges to them. Things that are not polyhedron are your cone, sphere, cylinder, because they have a curved edge to them. So very similar to the definition of polygon, where you could not have a curve on a polygon in 3D, you cannot have a curve on a polyhedron. A lot of what we talked about on Friday were different types of polyhedron, but we didn't use that term. We were specifically looking at some of them being prisms and pyramids. So all those models you see behind the smart board and a lot of the ones that were up to your left, just in general, polyhedron. They're three-dimensional. Every face is a polygon. So that's the three-dimensional name. And you can name polyhedron just by how many faces they have. A lot of the same prefixes, like a cube. How many faces does a cube have? 6. What's the word for 6 in polygons? Is it a hexagon? So instead of hexagon, it would be hexahedron. It'd be a polyhedron with 6 faces. So an octahedron would be a three-dimensional shape with 8 faces. That would be, or at least one possibility of the gray model that is up there. So that's what you do with polygons in the naming, if they are not a prism or a pyramid. Okay, what we're going to do is see, there's a pattern as far as how many faces, vertices, and edges that a polyhedron has. And did anyone research Euler in here? Euler? That was your mathematician? Okay, you might have come across this formula as you were researching it. Okay, what I need is some data. I need a count of faces, vertices, and edges. How many faces, vertices, edges? Count vertices, faces, edges. Let's do it. There. Count that one up. How many spots? I had 5 spots. Okay, we'll have those 5 people count up how many vertices, faces, and edges. Oh, we got 2 models that are the same. Find a different one. They can help me around. How many vertices, faces, edges? I think 2 of you had triangular prisms. Okay, so triangular prism. See if you agree. 5 faces. Okay. Edges. 9. Vertices. 6. All right. Kenna has a hexagonal prism. 8 faces. Well, oh wait, no, sorry, 18 edges, 12 vertices, okay? We got trapezoidal prism. Okay, how many faces? 6. Edges?
12.
Vertices?
8.
Okay. Then we got a pentagonal pyramid. Okay, what do you got, Sam?
6 faces, 10 edges.
Okay. And then Megan picked something she thought looked kind of cool, if you can see what she's counting up there.
I have 14 faces.
14 faces. And I'm going to call it a polyhedron because it's not necessarily a prism or a pyramid, and she needs to do some more counting.
Right, while she's counting, let's see if we can determine, there is a pattern as far as how many vertices, faces, and edges there are. And it has to do with adding two of those columns, vertices and faces, or edges and vertices. Add two of them and then see how it relates to the other column. There's a consistent relationship. How many? 28 vertices, she thinks? Okay, so those of you that aren't counting, add up like two of these columns and then compare it to the other column. Let's see if you can find a relationship. Who's finding a pattern? Jack's got one? So maybe we can tell you what your last number would be, Megan, here, if they get this formula. As long as your first two counts are right, I really don't, I can't verify that. What'd you see, Jack?
The number of faces plus number of vertices, it's 2 more than the number of vertices.
Okay, faces plus vertices is 2 more than the edges. So if we took edges and added 2 to it. Faces and vertices, 5 plus 6 is 11. That's 2 more than edges. So maybe if I subtract 2, that would give me the edges. 8 plus 12 is 20, subtract 2 is 18. 6 plus 8 is 14, subtract 2 is 12. 6 plus 6 is 12, minus 2 is 10. So if Megan gave me the first two numbers right, 14 plus 28 is 42. Subtract 2, 40. She should come up with 40 edges if her first two were right. And what you might have to do is count up.
You guys need to like mark it.
Yeah, if you could mark it, but I don't want you to mark up the whole thing. But I would agree, it's kind of hard to do. So when you pick that one, I kind of want to. Okay, what we just discovered here was what Euler came up with. Now, he might have written it a different way. The way that I have on the wall here is if you take the vertices minus the edges plus the faces, it will always equal 2. Vertice count minus the edges plus the faces equals 2. Or in a different order, vertices plus faces minus edges will always be 2. There's different versions of it. And actually, Basic Geometry's textbook and Regular Geometry's textbook show it different ways. But this is Euler's formula. Which way do I have it on your notes? Did I put it? I've got a lot of different ones. Okay, so the first one is the addition one, and the other is a subtraction, but subtracting equals E. Okay, so anyway, I must have put the Basic Geometry one on the wall. But you can make different versions as long as you know what this formula is standing for. The count on the vertices, the count on the edges, the count on the faces, and then the 2 is the constant relationship that you always have. You can put the lines back up here if you wish. Okay, so what we're going to do with that is figure out how many vertices, faces, and edges there are on certain polyhedron. And it looks like Euler, but because of the country and how they say things, Euler is actually how you pronounce his name. It says, find the number of vertices, edges, and faces of the polyhedron. Use your results to verify Euler's formula. So this is the one that Megan McKenna. Boy, weekend. Counted up. So she's got 6 vertices, 12 vertices, 8 faces, 18 edges. Now when it says verify Euler's formula, what I want to see on your assignment is that you are telling me which version of Euler's formula you're using. Put in the numbers and make sure that I can see that the left side calculates to 8 or to 2. When you go 12 minus 18, negative 6 plus 8, So don't just say, yes, give me some evidence that you checked the Euler's formula. Okay, so that one we already counted. I don't think anyone counted this pyramid. Okay, so why don't you count up in your mind how many vertices, edges, and faces there are, and let's make sure Euler's formula is correct for it. So the verifying helps you know whether your count is correct. And this is why you would need those dashed edges so that you can see the other edges and vertices. You have to visualize the 3D for the faces. But how many vertices? 5. How many edges? 8. There's 4 around the bottom. Then there's 4 that go up from the corners to the top. And how many faces? How many flat surfaces? 5. So then to verify that those counts are right, check in Euler's formula. And 5 minus 8 is -3 plus 5, so that is 2. All right, this one is the gray model that's up to your left. Visualize what that is. Why don't you count the vertices and the faces and calculate the edges? So count the vertices and faces, those are pretty easy. And use the formula and calculate how many edges there would be. How many vertices? 6. How many faces? 8. So then to calculate, I'm going to use the formula that's on the wall. Okay, 6 minus e plus 8 equals 2. 6 plus 8 is 14. 14 minus what is 2? 12. Finish it solve, or finish solving in a different way if you want. 12 edges. There's 4 going around the middle. There's 4 going up. There's 4 going down. That would be 12. So that's another way you can use the formula, is to find the missing count. All right, that's one formula related to 3-dimensional shapes. Doesn't work on like cones or spheres because you don't have like the edges to count and the vertices. But this would be for any polyhedron. All right, let's skip on to the next formula. Okay, another formula is how you can come up with the diagonal of a prism, a rectangular prism. This formula can't be used for every shape, but for like a box, it can. And what we're going to do is try and find the diagonal. The diagonal goes like from this point across the box to that back corner. So think where the diagonal is. Let me grab a box. The diagonal is not just on one face. Nasty box. The diagonal doesn't go just on a face. That would be the diagonal of the front. When we're talking the diagonal of the prism, we're going to go from this corner to the bottom back corner, going through it. So to come up with that the long way, you could do Pythagorean theorem a couple times. You kind of see some things shaded out there. Oh, let me go back one. No, this is the one I want. You could go Pythagorean theorem a couple times. This is kind of the long way. Because if you know the length and the width, you could use the Pythagorean theorem, the length and the width, to find the distance across the bottom diagonally. Then if you would use that length and go perpendicular up, that would form a right angle. And the diagonal that you're interested in would be like the hypotenuse of it. That would be like the X, the H, and the D. Those would make another right triangle. So you could find this diagonal length using Pythagorean theorem twice. So what the formula has done is put this Pythagorean theorem with the second Pythagorean theorem, and we find out that to get that diagonal squared, you square the length, the width, and the height, and add it all together. So then if you wanted just d, and you know what d squared is, you can square root to come up with it. So this is how they came up with the formula. It's using the Pythagorean theorem a couple times. This is the form that's useful for us. To find the length of that diagonal, you square the length, the width, and the height of your rectangular prism, add it together, and square root the whole thing. That tells you the longest thing you could put in the box. It has to be pretty skinny to fit corner to corner, but that would do the diagonal it's involved. I want you to calculate one. Or a couple probably. Find the length of the diagonal. Your box is 6 by 8 by 10. And it really doesn't matter which one you call the length, the width, or the height, because you have to use all three dimensions. So your formula says square the length, add to it the width squared, add to it the height squared. Square root the whole thing. That'll give you the length of the diagonal. Since there's no rounding directions, probably a reduced radical. Got 36 plus 64 plus 100, root of 200. Should be coming up with the square root of 200, which should, oh, I put a decimal, should be 10 times the square root of 2. What if it were a cube? What would be the longest thing you could put inside a cube? It's the length of the diagonal. Length, width, and height are all the same. 25 plus 25 plus 25. Square root of 75, it sounds like. Reduced and radical. 5 times square root of 3. Not doing her calculation, she's drawing. That is three-dimensional. Okay, so that's a formula that, as I said, is just specific to rectangular prisms of some kind. All right, I'm gonna go on to this. You wondered what this thing is. Well, it's a three-dimensional axis. We've got X, Y, and Z axis. Now, you live in a three-dimensional world. Not everything's flat, so there is depth to it. So I want to introduce you to the XYZ axis, and there's a couple formulas. There's a distance formula and a midpoint formula. You probably see them at the bottom of your notes there. A midpoint formula and a distance formula for 3 dimensions is very similar to those formulas for just 2 dimensions. So how is it different? It has a Z part to it. And I did not change the formulas on the wall, So as you look at those distance formula and midpoint, it just has the same thing as up there with an additional z portion. So what's the x, y, z? We've got length, width, and height. So when we work with the three-dimensional axis, instead of an ordered pair, you're going to have an ordered triple. And an ordered triple, I guess there was one on here. 3, 2, 4, that's an ordered triple. That tells you the amount to go on the x-axis, the y-axis, and the z-axis. Now, if you work with the CAD program, I think the order of the numbers is not the same as what's in the math setup. So I don't know why it's different, but the computers use a little bit different setup. But the x-axis is forward and backwards. I'll write that down. Okay, so the first number, the x-axis goes forward and backwards. The y-axis goes left and right. And then the z-axis goes up and down. So I might ask you to tell me how you would locate the point 3, 2, 4 on a three-dimensional axis. So what you would say is the 3. So we would go 3 units on the x-axis. So would that bring us forward or backwards? Forward is considered positive. So forward 3 units. 2 as the second number. The 2 is the y-axis. Would that take you to your left or right? To the right. So forward 3, to the right 2, and then the 4 at the end would be up. So go from here up 4 units. So out in space, the top of my eraser here would be the point 3, 2, 4. Now that's really hard to show on a flat paper. Okay, that's why the dashing is kind of in there to help you. Okay, coming forward, over, and then up. It really works better if we picture a whole box maybe there instead of that. So there's a box for you. Now, where is that positioned? Well, one corner of the box is at 0, 0, 0, and then it's on the positive y, the positive z, and the positive x. Why don't you grab the Kleenex box here? Actually, my box back there. Okay, so where is that positioned? 0, 0, 0 is going to be this back corner, and it comes forward a certain amount, to the left a certain, or to the right a certain amount, and up. Now, which way? I guess that's about the same dimensions. So what does that 0, 0, 4 indicate? That's going to be this point up here because it is forward nothing, so it stays at the origin. By the way, the origin is 0, 0, 0. So it stays there, doesn't go left and right at all, goes straight up 4 units. So without really looking up there, can you tell me what the point out here would be? I think the dimensions are 3, 4, 5. So to get to this point, from 0, 0, 0, we have to go forward. How far? 5. Left and right? Nothing. Up? 4. Okay? So 5, 0, 4. How about the one that's in the back here, top one? Forward and backwards, how far? 0, okay? It's flat with this back part. Okay, left or right? I go 3, and it's the positive or negative? Positive. Now if it were over here, that would be going negative 3. All right, so back to where it was. So 0, 3, you have to go up 4 to get to this point. If I would put it back here, what's that same top point's coordinates? Forward or backwards? Negative, it's 5, that's what it would be. Negative 5, then go to the right, 3, and up, 4. So negative 5, 3, 4 would be that point. So if you think about what it's equal with, that can help you get the coordinates figured out. So a three-dimensional axis you will use, especially when you get into calculus. You'll do a lot with three-dimensional axis because that's what calculus is kind of based on. finding the area of curves that are three-dimensional. So I want you to try, can you draw a picture of a cone on a XYZ axis? Why don't you just start drawing a cone? Draw a cone, maybe off to the side there. And the height is 5, the radius is 3. So probably about as wide as it is tall. And we want to position that on an XYZ axis. And we want the base centered at 0, 0, 0. So here's 0, 0, 0. There's going to be an axis going up, an axis going this way, and for three-dimensional, there's an axis coming forward. Now those are just the positive parts. If you want to dash the negative parts of them, I think that one coming forward usually is about like a 30-degree angle. Okay, let's see if we can figure out the coordinates. This point is 0, 0, 0. Okay, what's this point on the edge of the cone? Read the information. The radius is supposed to be 3. So how far forward from the origin or backwards? 0. Left or right? 3. Up or down? Nothing. How about the top point of the cone? Forward or backwards? 0. Left or right? 0. Up? 5. How about this point? 0, -3, 0. I know it looks weird, but how about the front? I guess that wouldn't be it right there. It'd be over here. I got rid of way too much there. Okay, so what's this point? I think where that is, if I've got a circle here, how far forward does it go? The radius of 3, 0, 0. Yep. 3, 0, 0. And how about the one that would be back here? -3, 0, 0. All right, you guys are getting the idea. Okay, so a little bit on your assignment for related to the three-dimensional axis, and I want to make sure I've at least shown what those formulas are. So as I mentioned on your notes, there's a formula for distance and midpoint. So distance, if you want to find how far, you could have slanted all kinds of lines here. How far are these 2 points apart? You can do the distance formula with this endpoint and with this endpoint and see how far they are apart. That distance formula simply is like the one we had, but it also has the z component to it. Is that in your notes? Okay. And then there should be a midpoint one. To get the midpoint, you know, what's halfway between, you would have to go forward or backwards half as much, left and right half as much, and up and down half as much. So that midpoint formula, I guess I've got both of them here. The midpoint formula, you're averaging the x's, you're averaging the y's, you're also averaging the z's. So same formulas that we had before. But what's it going to look like when you calculate with them? That one's got all zeros in it. Let me skip that one. It seems too easy. Let's get some positives and negatives. No, there's positives. So to do the distance formula, you would be subtracting the x's. So this 4 minus that 6 and square it. And then 6 minus 11 and square it. 12 minus 3 and square it. So square each of those. Add together. You've got the square root of 110 said nearest tenth, so about 10.5. So read the directions to see if it's decimal or radical. And then the midpoint formula, you're gonna add the two x's and divide by 2, add the two y's, divide by 2, add the two z's and divide by 2. So what point's halfway in between there? 5, halfway between those, 8.5, 7.5. If we had more minutes, I'd have you completely do one on your own, but I think you would be able to understand what that means. All right, we had a lot of checking at the beginning. The assignment for Monday, or for today, is, I know it's on the backpack, but let me write it up here. Page 674. 1 through 5, 7, 10, 12, 13, 28 to 31, 52, 57 to 59, 64, 65. So a lot of single problems there.
So since I was gone Friday, I'll get that assignment and today's assignment by tomorrow.
By tomorrow.
Yeah.